The labs just get bigger.
Yeah.
It's gonna be a book soon.
Yeah. I think that's the thickest one.
This is the thickest one?
Yeah.
Are we not general chemistry?
I know. This is the one that question was. I will let you know in a second, sorry. Oh, this electronic configuration, before you go to the 14s, right, you do FD1.
Yeah, but then if you go back and fill it up, you want to like
Put them together.
Yeah.
So it'd be FD10.
10. Yeah.
Right there instead of that. So
Yeah.
it'd be FD10 F14.
Yeah.
Okay.
Yeah, that's the only thing that's like confusing is you just do the one and then you fill out the rest of the 14 and then you go back.
Because
So, yeah,
like
you don't
if you're
have to
reading it like a book,
Yeah.
that's kind of how I was writing it. But so instead of that, like if it fills it up, put it before.
Yeah.
Okay. But so if it were like 7, would you still put like 7 right there?
Yeah, so you just, yeah, if it was 4, 14, and 5, 7, yeah. And I don't care too much about the order, like the first one, the 4, F, and the D, like,
Okay.
that's not what I'm concerned about. I'm more concerned about the usage.
But don't write like
Yeah,
5D
you don't want to
twice.
separate it, yeah.
Okay.
And then it looks like there's 11 electrons in the D.
Yeah. Okay. Okay.
It like, says it, oh my god, when this is anything happening. Oh my gosh. Yes. Oh, this is. For real. I'm gonna try to do it today. Try. I found it.
All right, let's go ahead and get started. So I'm a little behind on grading. So I've caught up on the homework, but I haven't graded the labs. So I know some people were asking about labs. So yeah, I have them. I just didn't physically grade them. And then there's one chapter 3 homework that has no name on it. And I can't recognize your handwriting yet, so I'm not sure whose that is. So check that out. All right. And then a couple of reminders that our midterm is next week. So our midterm is on Wednesday. So right before Halloween, you get a scare. And so we are going to review, though, on Monday. So we'll go over practice problems on Monday, just kind of take that time to review, answer questions so that you feel really good for Wednesday.
This Wednesday?
Next Wednesday, yeah. Yeah, so next next week will be a review. So like I said, review Monday, kind of, recap everything, and then, yeah, exam on Wednesday. And then again, just email me if you haven't already about makeups or if you're traveling so we can send it to the testing center or whatever we need to do. Any other questions, comments? All right, so now let's get into our covalent bonding. And so our lab really builds on this. And so, let's just put a little refresher too, because we had been discussing ionic compounds. So, we said, well, ionic compounds, and these are generally our salts, right? That's like the other name for them, our salts. right? We could list a few examples, but then again, the key point is that we actually transfer electrons over. And so we want to kind of contrast that idea with our covalent bonds. And so now we're going to be looking at our covalent compounds. And so these can also be like more generally referred to as molecules, right? When we just kind of talk about molecules, we're generally referring to our covalent molecules, kind of discrete. And right, we can think of examples, drug development, any sort of thing. So those are all molecules. And so, of course, let's get into how we can construct our covalent bonds. So we'll learn about our bonding pairs. So these are just defined as electrons that are shared by atoms. And so again, we've kind of gotten a small taste of that. And we'll kind of look at, the why. And so now we're kind of starting to build. And this is a little bit more advanced, but I want to at least show this depiction because we want to think about, again, several things, right? So we have to think about, well, what's actually coming together? And so even with our simplest molecule here, so H2, right, atomic hydrogen, so molecular hydrogen. So we're thinking about our orbitals, right? So we're bringing in our 1s orbitals, so each hydrogen is contributing 1 electron. And then so kind of the fundamentals of bonding and what's happening is this combines to make a new molecular orbital, or MO. And again, this is kind of going beyond this scope, but we want to show, well, why is it favorable to make these bonds? And so we're looking, again, energetically, right? So now these 2 electrons are going to be in a bond there. So that's basically representing that right there. And then we have our corresponding anti-bonding orbital. Again, that's kind of beyond the scope of this course. If you were to take the 200 level series, we do, again, talk about MOs in depth. And so we're just saying, okay, these are bonding, and this would be formerly anti-bonding. And so this explains why helium doesn't exist, but that's, again, kind of going beyond the scope. And helium as a diatomic, I mean. And so, again, what we want to take away is kind of our Lewis dot structure representation, right? We had 2 hydrogens, and then we're going to see, again, how they come together to make our bond. So that's our bonding electrons, our bonding pair. And so, right, each line represents 2 electrons, just to reiterate that. And so we may also find lone pairs. And so lone pairs are just electrons that are not shared by the atoms, sometimes called non-bonding pairs. And so let's kind of break this down, again, how this is working. And so let's look at this water molecule. And so start off, though, so just write the Lewis dot structure for oxygen. See if you can do that. So what does our Lewis dot structure for oxygen look like? You can kind of shout it out and describe it. What does it look like? So 6 valence electrons, And so we should have something of like 2 dots together, right? And then the last 2 are kind of by themselves. And so again, it's really simple, but also powerful what we're looking at, right? So now we're seeing, okay, well, these are probably my lone pairs, right? So notice they're already paired up. So lone pairs, or again, kind of our non-bonding pairs. So we can already see, all right, these are probably not going to be interested in bonding. But then we have these 2 lone electrons over here. So again, this is giving us a hint that it wants 2 bonds, probably. And what do you know, right? That matches with what water is, H2O, right? So those 2 hydrogens are going to attach there. I'm just going to redraw it. So we can, again, look at those electrons. And so this is also kind of tied in to your lab. And so kind of, again, the other key thing is you want to make sure you take the correct number of valence electrons. So we have 6 from oxygen, and then each one of our hydrogens contributes 1. And then again, we can see how, right, those are going to come together to make our bond. I'm trying to draw little half arrows. So half arrows indicate 1 electron movement. And then again, right, that's how we get our bond. So our 2 lone pairs, and then of course, right, just like we predicted from our Lewis dot structure, those single electrons went into our bond there. So again, right, hydrogen contributes 1 to the bond, and oxygen contributes another 1. And so this is just another note. So this is called a normal bond as well, when you have each atom contributing 1 electron. So we'll mainly see that in here, but I'll point out again when we don't have a normal bond. All right, so now we can like re-look at the diatomics and understand, well, this is why they are diatomics. So we looked at hydrogen. Now let's do fluorine. So again, we can start off with our Lewis dot structure with our 7 valence electrons. And again, write this 1 little dot out here. So that's signifying it's probably going to make 1 bond. You can also think about the electron configuration. And again, right, drawing that out if that helps. And then, so comment in the chat, just starting to talk about geometry a little. So, yeah, we'll start talking about geometry just a little bit. I'll also bring kind of a geometry cheat sheet. And so that's also what we want to look at. So you can kind of tell that this has like a tetrahedral base shape, and then it ends up being bent. So now the geometry is bent here, which again, we'll kind of revisit this geometry. All right, so looking at our diatomics, again, just filling it in, whatever is kind of useful for you. Again, right, get yourself used to looking at all these different representations of the same thing, right? So we can again see, okay, I have 7 valence electrons, right? Again, we can see 7 valence electrons, 7 valence electrons here. And so again, right now we're pointing out, okay, it probably wants to make a bond here, right? It either needs to gain an electron from a metal, or if it's going to be bonding with itself. Now we can see, again, where it's going to want to bond, and it's going to be bonding, right, using the p orbitals. So that's also kind of giving us, again, beyond the scope of this course information, but you can kind of see, like, where the higher level information is going to come from, right? You're not really learning anything revolutionary if you go to the 200 level class. You're just kind of seeing it in depth again. And so again, same thing. These fluorines can come together. We can understand why they have just 1 single bond between them, right? They just needed 1 more to fill the octet. And so now look at how to analyze this. So now we can see, right, this fluorine here feels all these 8 electrons, so 6 directly bound to it, right? We can say we have 3 lone pairs on this fluorine, and then, so 1, 2, 3, 4, 5, 6, 7, 8. So, okay, octet rule fulfilled. And then our second fluorine, right? 1, 2, 3, 4, 5, 6, 7, 8. Looks good. And then, so we should only have 14 electrons total in this system, right? Because we have F2, and you can do some accounting on the side. And so we said, well, each fluorine has 7, so times 2, so there should be 14 electrons. And so then, right, double check yourself, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And so that's the important thing, is you want to have a correct total electron count. And then, of course, trying to understand the geometry and all that comes next. All right, so now practice it for oxygen. So see if you can draw out our Lewis dot structure now for oxygen, right? Start with the Lewis dot if you need to, and then kind of put it together. How many bonds does it have? I'll pass out some more work. Yeah, it was what it is. So I'm faster with the homeworks and then slower with the labs. Yeah. Catch up on your class. Yeah. I was trying to say how I did your shift with them. Oh, yeah, you got it.
Is it wicked?
All right, so I'm seeing some good things as I kind of walked around. I was creeping on people's papers. And so, right, you could have started off again with our Lewis dot structure. So 6 valence electrons again. And right, this is kind of our hint. Well, it probably wants 2 bonds. And then especially, right, if we're putting another oxygen with it. So now, okay, that's our hint, right, that there's probably a double bond. And so now we can kind of put these pieces together. And then also use, right, your valence electrons. So we said oxygen, okay, 6 valence electrons times 2. So now there's 12. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that looks good. And then, right, double check yourself. Okay, so this is 1, 2, 3, 4, 5, 6, 7, 8 that it's feeling. So that looks good. And so this oxygen, so 1, 2, 3, 4, 5, 6, 7, 8. So that looks good. So now try that with nitrogen real quick. So now do the same thing, right? But now N2. And how many bonds do you predict that nitrogen will have? So double check your structures. So I'm kind of seeing not enough bonds between them. So you can start off, right, your Lewis dot structure of 1 nitrogen. So there's our lone pair, right, 5 valence electrons. So then what do we predict? What type of bond do you think is between the 2 nitrogens? Kind of based off of this, maybe off of your structure. So single, double, triple. So I think I see 3. So double check, right, your double. And so this is where, again, you can kind of play with your electrons. And so if you had only started off with a double, and again, right, this is where your total number of electrons comes into play. So of course, 5 times 2 is 10. And then again, right, just kind of play with it. So, all right, 1, 2, 3, 4, 5, 6. And then what if you did 7, 8, 9, 10? Oops. Let me redraw that so it doesn't look weirder. And so, right, this is where I'm also saying, like, it's about the process, right? And not just about getting the correct answer. It's okay, let's look at this structure and figure out why it needs to be a triple bond and why this structure isn't good enough. And so first thing you do is, well, do I have the correct number of electrons, right? Because I said that was the most important thing. And so, okay, we have 10. But now if we do our analysis, right, so you can see, well, this is only filling 1, 2, 3, 4, 5, 6. So this one doesn't have enough. And this nitrogen, right, okay, it has 1, 2, 3, 4, 5, 6, 7, 8. That works, but we might need to move it, right, to share it. So then you can kind of take these electrons and move them over here as kind of a bonding pair. And then, okay, this now gives us a fulfilled octet. And so, yeah, that's like the next important thing is after you have the correct total number of electrons, do we have a fulfilled octet? And again, right, this Lewis dot structure, though, is already hinting to us that it's probably going to make 3 bonds. Or at least most likely, right? So it wants to make those 3 bonds. And so, yes, that explains why it's triple bonding with itself. And so now we can see, okay, now the left side is happy with the octet rule. The right side's happy with the octet rule. And we have our structure. And then what's so fascinating about this is, yes, right, this does give us the information. So fluorine does have a single bond. Oxygen does have a double bond. And then, right, nitrogen does have a triple bond. So all that can be reflected in the bond length. And so again, right, really powerful calculations with just these seemingly simple little dot structures. And so then there's how do we predict the type of bond? And I think some people might have asked this before, maybe not in this class. Again, I get my 2 classes confused. But really, so again, bonding is kind of this spectrum. And so we just kind of have the difference of electronegativity as kind of a guide. And so we can kind of see this. And so again, right, think back of our other definition. So we said ionic compound was we have a metal and a nonmetal coming together. And then it mentions that we have, right, this really large electronegativity difference. And so we can see this. And so again, like we mentioned, right, the electronegativity scale is on here. And so again, this is from in a bond, right? We mentioned this back with our periodic trends. Does that sound familiar? So, right, our electronegativity is how much an atom is pulling in the bond. And so we're seeing, right, basically the difference in electronegativity. And so if we look, and you would have to be given, right, a value, these values or this chart on an exam. And then, of course, values could vary slightly. So fluorine, again, is considered the most electronegative. Usually it's considered to be 4. This has 3.98. And then we could do an example here. So if we look at ionic with sodium chloride, so again, all we do is we take our difference here. So chlorine is 3.16. And pull up my calculator. So 3.16 minus our sodium, so 0.93. And so that's over 2, right? So a difference of 2.23. And so, right, roughly speaking, again, anything larger than 2 is generally considered an ionic bond. And then now, so if we look at, so a pure covalent bond, or completely nonpolar, right, is where electrons are shared equally. And so this could be true for fluorine, right, diatomic fluorine. So even though both fluorines are obviously very electronegative because they're the same electronegativity, right, there's no difference between them. So then we have a completely nonpolar bond. And then what's being shown here is our electron density map, so it's just showing you where the electrons are most likely to be. And so the clouds, again, are the same size, so they're even. And then again, right, this is just kind of the guide for this. So it's considered, once we get past 0.4, that now it's a polar covalent. So again, now we're just saying that we have some sort of unevenness in sharing of electrons. And so now this is also depicted by our probability density map. And we can see this large negative cloud. So this, let's say this is HCl, right? This is probably the chlorine then hiding in there. And again, showing that our electron density is on the chlorine. And then all we're really saying is, well, we can continue and have such a great difference in electron negativity that there's no unevenness in sharing, but rather it's just completely split. So does that kind of make sense to everybody? And so again, right, we'll do this for our purposes and just kind of mathematically, again, be able to compare and calculate these values. But just kind of know that on a research scale, that this is like what research is about, right? It's trying to determine, well, what kind of bond is it? How long is a bond? Like, is it a single, double, triple bond? Like, how are they bonding? So all these questions, right, could come up in research. So the answer is not always, you know, straightforward over what it is. So it depends on like the structure and how it's behaving as well. So this is just a pretty good guide. But that being said, right, chemistry is all about breaking the bounds. Just looking for questions. All right, so then kind of recap here. So we said we have a single bond when 2 atoms share 1 pair of electrons. And again, right, each line signifies 2 electrons. And then, of course, right, we're always talking about the octet rule. But then hydrogen, when you do the analysis, of course, that's the only one that's going to be fulfilled by the duet rule in a compound. So that makes sense, right? It only has the one S to fill up. So there's our duet rule. So we can see that in our water structure. And so like we saw for oxygen, so we have a double covalent or just a double bond, so 4 electrons, and then again like we saw just depicted by our 2 lines with every line meaning 2 electrons, so there's our 4 electrons there. And so these are elements that can typically double bond. And of course, carbon can do that. We'll see some funky stuff with maybe nitrogen. Oxygen does a lot of double bonding things. So you see that with like carbon, making those sorts of structures as well. And then sulfur, of course, is pretty similar to oxygen. So we'll see it doing double bonds. And same with phosphorus. So phosphorus can do funky stuff. And so then we looked at nitrogen. So again, our triple bond, or triple covalent, however you want to refer to it. And again, our 3 lines signifying our 6 electrons there. And so again, we'll see some kind of triple bonding scenarios as well. So carbon and nitrogen. So I think this is one of the compounds from your lab. So again, we can see our triple bond scenario, right? And we know nitrogen likes to make 3 bonds anyways. And then you can do some funky stuff with oxygen and sulfur sometimes. All right. Questions so far? So now let's kind of go through our geometry. And again, kind of our representative compounds, and keep kind of putting the pieces together. So let's look at our group 4. And so our group 4 compounds have this general MX4 formula like we're kind of seeing. Do I have a periodic table? No. And so looking at group 4, so right, that's all here. So so carbon, silicon, germanium, tin. And so what's a good classic example from group 4? Anybody think of one? Anyone come up? Well, the chat's got it. So CH4, what's the name for CH4? You may remember, it has a common name. So this is methane. So methane, CH4, so of course, right, simplest hydrocarbon. And so this is always the classic example. And then I like to practice our 3D structure. And so I'm drawing it 3D now. So these 2 hydrogens are in the plane of the board. And then if I draw this fat little wedge here, that means that it's coming out of the plane of the board, so that hydrogen's coming out. And then using our dash here, this is going behind the plane of the board, so that makes our tetrahedral structure. And then, so right, double check your electron count. So we have, right, 4 valence electrons from carbon. Hydrogen has 1, and there's 4 of them. So we should have 8 electrons total in this system. So 1, 2, 3, 4, 5, 6, 7, 8. That checks out. And then, of course, everything's satisfied by the octet or duet rule. And then we can name the geometry at least. So this is called tetrahedral. So that's this classic, again, 4 things kind of evenly distributed around. And this is on the cheat sheet paper, but I'll mention it. So the angle here is 109.5 degrees, and it's all even all around. And so then we can look at other classic examples. So now we have like carbon tetrachloride, or silicon tetrachloride, or let's see, germanium tetrabromide. You can go on and on. You can even make hydrides, silicon tetrahydride, although probably not be very stable. And so again, they all follow the tetrahedral pattern, except of course, the rest of them are going to have more electrons around them, just because they're not hydrogen. So this is carbon tetrachloride here, I'm just drawing. And then, right, you could replace in any one of them. So they all have that same pattern. And then don't forget your little lone pairs. any questions on kind of this so far? All right, so then let's keep going. And so let's look at group 5 now. And so we'll look at kind of two classic examples of group 5. And so first we can look at kind of their simple compounds, so kind of the MX3 formula. And anybody guess what a group 5 representative compound might be? Especially if we look at it. Group 5, what's a good one that kind of matches that MX3 formula? So the classic one is ammonia, NH3, right? So it follows that. And so if you look at its Lewis dot structure, so there's, right, it's lone pair. So it's saying, okay, well, it's probably going to make 3 bonds. And so then we can draw it out. And so it kind of looks like our tetrahedral, except of having an atom here, though, we have our lone pair. But then similar sort of geometry. So now our hydrogens are there. And so these would have a slightly smaller angle to compared to the 109.5, since the lone pair takes up more space, so kind of compresses these hydrogens just a little bit closer together. And so the geometry is trigonal pyramidal, or pyramidal. And then, so let's look at another, or some more compounds. These are all group 5. Oops. And so we could do PCl3. And so kind of the problem, though, or maybe not the problem, but what we can start to tease out as well is that these compounds are pretty reactive. At least a lot of these, especially like the phosphines. So phosphorus trichloride is going to be pretty nasty. Phosphine is just pH3, so that's pyrophoric. And so we can kind of tell why. We have a kind of a hint here. And so our hint is in this lone pair. So this lone pair, you know, it's kind of happy together, but it's also primed for action. And so let's actually look at some expanded octets. And so now let's look at kind of group 5 expanded octets. And so with these phosphines especially, so these phosphines are susceptible to oxidation. And again, right, this is, use your Lewis dot structure to kind of think about it and see what's going on. So now this phosphorus has these 2 electrons that it could do something with, right? And then you're kind of thinking about oxygen. And even take it back to its Lewis dot structure, right? So oxygen, well, it had 2 lone electrons, so that's my hint that it can make 2 bonds. And so we find that one thing that phosphines can do is, of course, oxidize. So they make compounds like this. And so right now this is one example of an expanded octet. And so now we can understand, well, what does it mean to have an expanded octet? Well, obviously we do our electron count, and right, well, first check your sanity. right? So phosphorus brought 5. Each hydrogen has 1, so times 3. So that's 3. Oxygen, right, brought 6. So now 8 plus 6, so we have 14 electrons. So let me not forget my lone pairs. Count it up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, we have the correct number of total electrons. Now let's try to figure out if the octet rule is satisfied. So, right, these are satisfied by the duet. That's fine. This is satisfied by the octet, right, our oxygen. But then what's funny about phosphorus? What's its total electron count? What do we count on there? Yeah, Marin? 5 bonds, so then times 2 gives us how many? So 10, right? So phosphorus actually has 10 valence electrons on it. And so when I'm writing valence electrons, I'm just trying to show it on the phosphorus. I'll re-emphasize that. And so that's actually okay. So it's kind of weird. And, well, now I have to give my slight rant because your textbook probably says something erroneous. And so usually, and I even kind of have it hinted on the notes here, is we have expanded octet, and we have a note here that it says third row main group. Okay, well, let's look at that. And so what it's saying is right here on the third group of our main group, right, 3p, that's where it can start. And then usually textbooks give some like erroneous definition of like, oh, once you get over here, they're invoking d orbitals. And that's not true. So I just want to say that they are not bonding with d orbitals. So they're still bonding with the p orbitals. And so really what happens is it's just a physical limitation problem. And so what I mean by that is we can look at other kind of compounds that exist. So PF5. And so this is, again, something else that group 5 can do, expanded octet. So group 5 expanded. And so phosphorus can make 5 bonds around it when it really wants to. And so I'll draw it. And so again, I'm trying to draw our 3D shape. So these 3 fluorines are all in the plane of the board. And then this fluorine is kind of coming out. And it's on the same plane as this one. And so this is trigonal bipyramidal for this shape, but you don't need to know that. But what we need to see is, okay, well, this exists. But then, right, the true question, and what I'm trying to get at, is, well, why doesn't NF5 exist? And so the problem with NF5 isn't that it doesn't have d orbitals, because, right, phosphorus actually doesn't have d orbitals, so that's a bad argument. It's just that nitrogen is so small that it kind of runs out of space. And so if you look at models of this compound, NF5, what you would get, and I try to draw it a little over-exaggerated, but you would have that basically the 2 fluorines on what's called our PZ position, right, our axial position, they would have to be elongated. So they would be a little long, and then, right, these fluorines would be a little closer, but it's just not really stable. So I think they might have isolated NF5 in like a gas phase temporarily. But yeah, it has nothing to do with the d orbitals. It's just now it becomes too small, and it just physically can't fit those 5 fluorines around it. Whereas, right, the phosphorus is large enough now, and so that's where we get this kind of, rule about third row main group. But I just want to be very clear that we're not evoking d orbitals in all this, that it's still p orbitals, right? We're just focusing on our valence electrons, but you hear that kind of everywhere. All right, so this would only exist in theory, but then other ones, so all the heavier analogs, of course, arsenic, and it doesn't have to be fluorine, but again, kind of same thing, so arsenic, pentafluoride as I'm drawing. That looks like so. And again, with all of these expanded octets, right, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So yeah, these all have 10 valence electrons there, which is okay. All right, going back to kind of our more normal stuff. So looking at group 6. So again, we drew that out with oxygen. So again, we're seeing it tends to make 2 bonds, at least a lot of the time. So we could draw that right with CO2. Get a structure that looks something like this. Again, right here's our 2 bonds, so that's a good hint. And then octet rule, everything's satisfied. Hydrogen sulfide, right, is an analog of water, at least geometrically. And so if it has this bent structure, of course, just like water, right, that is bent. So just kind of recognize that. And then again, carbon disulfide would be similar. And then I think I mentioned, again, the organic structures that you'll see with oxygen. So participating in 2 bonds. And then let's look at group 7 before we look at other crazy octets. And so, right, let's just look at chlorine for a second. So, right, chlorine looks just like fluorine. 7 valence electrons, so we can predict, right, chlorine itself would just be a single bond, like so. And of course, right, group 7 is all our halogens. We know they like to make 1 bond, at least typically. Again, we'll look at more expanded craziness. So HF, or any other halogens, right? Again, we saw it kind of in the silicon tetrachloride. So again, right, they're all making 1 bond to that. And so now let's look at some more octets. So now let's start with group 8. And so what's funny about group 8? What's already the funny issue here? Who's group 8? Yeah. So, right, they're supposed to be the noble gases, which we said, right, that they have an octet rule, so they're satisfied, or at least they should be. But then what we find that, again, of course, chemists are always trying to push the boundaries. And so you don't typically have neon compounds, probably for the same reasons why we don't have, like, nitrogen pentafluoride. But argon difluoride does exist. And so you could predict what its geometry would be. And so, right, this starts to get a little crazy. And so, yeah, chat is asking, so xenon also reacts. So we'll look at some xenon compounds. So argon, again, count your electrons. So argon has 8. Each fluorine has 7. So now 14 plus 8 gives us 22 electrons. And so again, for these, right, you kind of have to play with them. So I'm going to just start by making a bond there, okay? And then I'll fulfill my octet rule for fluorine at least, because that's easier. So now, where am I at? So 8, 9, 10, 11, 12, 13, 14, 15, 16. And then now 16, 17, 18, 19, 20, 21, 22. So we have something that looks like this, and then this would actually be linear. And so somebody mentioned xenon. So yes, xenon is our other kind of classic example. So xenon also does difluoride, but see if you can draw out the structure for this other one. So xenon tetrafluoride. So kind of sketch that out. What do you think that looks like? So take a second. So again, just kind of sketch it out, right? So I'm just going through my total number of electrons, so 4 times 7, so 28. So it looks like we have 36 in this system. And then the fluorines end up being planar, so this is all square planar as a geometry. And then fill in our electrons. So now 32, 33, 34, 35, 36 there. It'll look something like that. And then, so starting to get into polarity as well, so we'll need to talk about that and keep talking about that. So in this case, so this xenon would be nonpolar, and that's only because, right, it has symmetry. These fluorines are going out in every direction, so it's all even, but we'll keep looking at this polar, nonpolar thing. All right, let's actually take a quick break, and then we'll come back and finish up kind of more expanded octets. We'll practice some more crazy things, but we're at our 10-minute break point. Yeah, so come back at like 2 o'clock, and then we'll practice more expanded octets, more funky stuff. everybody make it back. So let's look at some more funky octet stuff. So we looked at group 5. And so let's look at some other just oddities. So kind of back to group 6. So just like group 5 can have the expanded octets. So on that third row, we can do like sulfur, hexabromide, and so right, we can write our Lewis dot structure. It's going to have 6 bromines around it. So trying to draw the 3D shape here. So this is called octahedral. So that's pretty fun. And then I should have brought up, so it's a similar cousin, so sulfur hexafluoride. But this gas, so have you ever seen like people change their voices with like helium, right, to go make like a small voice? And so right, helium, of course, is less dense than air, so that's why your voice comes out high. But sometimes, and I don't generally advise inhaling gases though, because obviously, right, you could displace the oxygen in your lungs. But if you want to play with this, or you can watch YouTube videos of other people doing with this. But if you breathe the sulfur hexafluoride, it's a heavier gas, so then your voice comes out deeper. So if you just Google on the internet, I'm sure you'll find people that do that. But again.
Yeah, those tanks I heard are not the most sanitary thing. They keep gases in, so.
Yeah, I mean, I'm not worried about the sanitation. I just don't want to, like, you know, you could kill yourself on any gas, basically, that's not oxygen. Yeah, I mean, right? Because, like, literally any gas could displace, you know, the oxygen in your lungs, and, you know, you need fresh air. So that's always my safety tip is, like, right, don't play with gases too much. Same thing with, like, you know, people have too much fun with whippets and stuff. But, like, right, same thing. You don't want to inhale not oxygen gases. But yeah. Anyways, safety tip. And yeah, so again, octahedral geometry, but I don't think you need to know that. And then let's try some other funny stuff. So our halogens can also do this expanded octet. So see if you could draw the structure for this molecule.
Is there not supposed to be any dots on the, like, the sulfur and bromine?
Oh, I just forgot the dots.
I just was a little confused. And why wouldn't you, like, why would you have two of the, like, those ones? Like, why would you do this solid?
Sorry, what?
Like, you know, I don't know what the correct term for it is, but like the little, like, squiggly lines almost. So just the shields, yeah, those.
Oh,
Why
those,
wouldn't you make those solid?
I was just showing geometry. So if you make them flat, it just doesn't show like the 3D structure. So for our purposes, like I won't take off points if you just draw out 6 lines.
Okay.
But I'm trying to show here that these 4 bromines are actually in a plane. So they're like sitting on a square plane. And then those other 2 bromines, right, are on the z-axis.
Then why would you have 2 of those different ones instead of just the usual one?
These 2 thick ones, since we have 2, so right, you have to kind of imagine they're like both coming out of the plane of the board. Yeah, so because you have 2 like that, right? So those are the wedges, and then 2 coming out and back. And those would be, maybe the molecule kits would be good. And so this one, kind of go through it, right? So each one of these halogens has 7 valence electrons, so times 4. So we know we need 28 in the system. So then you could just kind of start drawing it out, right? So I'm just starting off by making a line to each iodine. And then I'll fill in the octet rule for the iodines. So then check where we're at. So 3 times 8 is 24. So then 25, 26, 27, 28 there. And then of course, right, this is just another example of halogen expanded octet. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So right, this central iodine has of course 10 electrons. Any other questions so far on kind of structures? And so again, right, what we're seeing is a pattern. So you want to just kind of start seeing the pattern of, again, right, our group 4, group 5, group 6, group 7, and then of course just trying to put together all the expanded octets. And so now we're going to kind of look at this again. I'll look at geometry. Sorry, question. Are you asking about the II3 still? So with the II3, right, the most important thing is, again, total number of electrons. And so that's where I just started off with, right, you just try to make at least a single bond to each one, and then fulfill the octet rule on each iodine. So just getting 8 on each one. So then 8 times 3 gave us to the 24. And then that's how we got to 2 lone pairs on iodine. All right, so let's skip to our geometry then. So I threw out like a bunch of geometries, but then for our class, right, we just want to focus on a few examples and kind of the classic examples. So these are the only geometries that you need to know. And so we actually kind of skipped one group, but let's go back and do this group now. And so now we'll talk about group 3. And so group 3, I think we mentioned before, is a little funky. So let's look at our periodic table. And so I've kind of mentioned this in the past, but it's group 3 here, so boron, aluminum, gallium. And some of the funky things that we mentioned was that these compounds, right, they're over here in kind of the metalloids, but they really behave more like covalent compounds. And so we see that. So we have a lot of what are called boranes, so BX3. So borane, of course, is flammable, and all these boranes are flammable and reactive. So it could be boron trichloride. So again, all these are trigonal planar, and we can see that since they don't have any lone electrons. And so that's where, right, the funkiness comes into play. So now instead of the 8 electron rule, we're essentially deficient at 6 electrons, which again is okay for this group. It's only 6 valence electrons. And again, right, do your electron accounting to figure out how we got here. So I kind of, just slapped it out, but we can see where I got it from. So boron, again, brought 3. Each chlorine brought 7, so we have 24 electrons in this system. And so then, right, just drawing a line to each chlorine and then filling the octet. So 1, 2, 3, 4, 5, 6, 7, 8 for each chlorine. So 8 times 3 gives us 24. And then, yes, right, boron is deficient. And so that's telling us, okay, well, that's why all these things are super reactive, because they're going to react with oxygen. And so boron is going to make some oxygen bonds later. So note that, right? So all your group 3s, so aluminum trichloride 2, or tribromide, we'll switch up our halogen here. So all trigonal planar. And so again, right, I've drawn them as such. So just drawing our lines out on our piece of paper, saying these are all in the plane of the board. So yes, they're all sitting flat. So that's important. And then other things that are also trigonal planar is if it just has kind of 3 things coming out of it. So even this molecule, I'll draw formate, but really any other carbon with 2 things on it. So this would also be trigonal planar. And so that, again, kind of helps you see how things will interact. So you know this is sitting flat. And then, so tetrahedral, what was our classic example again? Did we already forget? Methane. So yeah, so just remind yourself of that. Okay, we have methane as our classic example. I'll give another one that we haven't quite talked about. Well, let's actually look at this. So see if you could draw the Lewis dot structure for ammonium now. And think about what happens with this plus sign, right? So you're losing an electron. So what does that do to your total electron count? So just see if you can sketch that out, and then we'll go over it. Yeah, you have a structure?
No. Are you losing an electron from the nitrogen and then 1 each from the hydrogen, so you're losing 5 total?
No, so you just lost 1 electron from the plus sign. So I'll give people another minute or 2 before I reveal all. So kind of looking in the chat, I think I got it figured out, but let's go over what we do, right? So again, let's look at our total electron count with our valence electrons. So we said, okay, nitrogen brought 5 to the party, then each hydrogen brings 1 times 4, so we're at 9. But then, okay, we have this plus sign, and so this is just saying that this whole species has a +1 charge on it. And so for electron bookkeeping purposes, so if I put a plus charge, then that's subtracting an electron. So then we have 8 electrons in this system. And then from there, you should be able to draw it out. So we just put a line to each hydrogen. And there are 4 bonds giving us 8 electrons. And then you just want to put a little plus sign, though, showing that, okay, this whole system is, again, with a positive charge. Or what we can also say, and so this is getting into a little bit more advanced how to analyze our structures. So we have what's called our formal charge. And so let's talk about formal charge. So formal charge is just, again, a way of like electron bookkeeping, so trying to figure out where the charge is. And so it's just defined as where you take the number of valence electrons, so basically like from your periodic table, and then you subtract the number of bonds, and then I always write minus the number of lone electrons. So like each individual one. And so what that is saying then, if we go through that together, so okay, for nitrogen, let me pick a color. So looking at our nitrogen here, so right from the periodic table, we know nitrogen always has 5 valence electrons. And then minus, so in this case it has 1, 2, 3, 4 bonds. And then right, there's no electrons on there. So minus 0. So then that gives us a 1 plus charge. And so we can put our little plus sign on the nitrogen. So that is telling us that the nitrogen is essentially electron deficient. So there's a little plus sign there. So either one of these is a correct representation. But it's a good habit to show where the formal charge is. And then the other thing about the formal charges is that they have to add up to equal the total charge of the molecule. But again, we'll revisit formal charge. It's like the last bit of advanced piece to analyze structures. All right, so let's continue with our recap. So what's our trigonopyramidal classic example again? Which one did we list here? Yeah, NH3 or ammonia. So again, right, think about what that looks like. Our lone pair sitting up here, occupying space. And then our hydrogens. So water would be bent. So water does kind of fall into the same tetrahedral family. It just has 2 lone pairs compared to the 1 of the trigonal pyramidal. So that's, yeah. Yeah. But yeah, same sort of, right, they still have that tetrahedral basis. It's just you're replacing the arms with lone pairs. And then let's look at another example. So see if you can try, and this is a bent one actually, but let's try SO2. What's that Lewis dot structure? So see if you can come up with that. So how's our structure coming? Anybody want to describe what our SO2 looks like? Mm. Well, just sketch out, so how many bonds did you get between the two? Like the sulfur and the oxygen? If you got two, yeah. So did you get that for each one? Between each sulfur and oxygen? So I see some nods. And so, yeah, I'm kind of getting some ideas here. And so let's kind of go through maybe how you went through this. So we're still kind of piecing it together. So you should have gotten something with 2 bonds on each one. But again, let's go through the process. We have some people kind of, I think everyone's kind of getting there, it sounds like. But yeah, let's just piece it together fully. So right, all of these have 6 valence electrons, so times 3. So we're at 18. And right, so again, just kind of play with it, because you don't know the correct answer right away, right? So maybe you start with just a single bond to each one and fulfill the octet for oxygen, right? Again, I'm just playing with it right now. So then you just want to see where we're at. Okay, 1, 2, 3, 4, 5, 6, 7, 8. So 16. And then, okay, let's make this 18 at least, right? So maybe you got to here. So this, again, isn't a bad point. But let's analyze, okay, how did other people get those double bonds? And so we start looking at it. Okay, well, oxygen's fulfilled by the octet rule. But sulfur only has this 1, 2, 3, 4, 5, 6. So that's not really great. And so, right, we could move kind of 1 over and now compare. So now I'm going to draw my new structure. Again, we're just kind of seeing how does it look? Am I there yet? And so now let's look at this structure and kind of what's wrong, what's right about it. And so this goes back to formal charges. So let's make sure we got our total number of electrons, right? So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay, that's fine. But then we have, so octet rule satisfied, octet rule satisfied, octet rule satisfied. Okay, that looks good. Now let's check our formal charges. So let's do it for oxygen first. So oxygen, again, from the periodic table, so I'm just going back to this formula, our formal charges. Okay, so oxygen has 6 valence electrons minus 1 bond, and then minus, again, when I say lone electrons here, I mean every individual one. So 1, 2, 3, 4, 5, 6. So that gives us a -1 formal charge. And well, if we have a -1 formal charge, we have to have a positive somewhere. And so let's look at sulfur. So sulfur is 6 minus 1, 2, 3 bonds minus 2. So that gives us our 1 plus. And so, okay, that's okay, but it's not really considered ideal to have a positive formal charge next to a negative formal charge. So that's why maybe the best answer is to then make that double bond. So then you have kind of our final structure that, again, many people arrived at, but my point is, right, this is an okay structure. On an exam, you'd want to put your formal charges, but this would be still correct, again, as long as you have the formal charges and your electrons. And then, again, right, compare this structure. So, okay, this is good. We've minimized our formal charges, right? So now we no longer have a formal charge. So now it's, let's just do it for completion's sake, right? So it's 6 minus 1, 2, 3, 4 minus 2, so that gives us 0. And then just double checking for our oxygen, right? 6 minus 1, 2, 3, 4. Minus 2 electrons is 0. All right, so we balanced out formal charges. Yes, the octet rule, though, is now violated, right? So now 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that is violated, but it's okay to do that, you know, with sulfur. Or, again, our third row. And so that kind of goes back to this thought, too, where these structures, right, they're not perfect, but kind of that's where we have these resonance structures, and we can kind of show that the average of these structures really gives us the true nature. And so, right, you could kind of say, well, maybe at some point oxygen does carry a little bit more electron density, right, since we have a negative charge there. Obviously, we could write the mirror image structure where the negative charge is on this oxygen. So again, just kind of telling you how it behaves, little hints. And so, yes, this is the best structure. And then all that to say is this is another version of bent. And so this is actually another degree. So this is a different degree. I don't have my paper in front of me. Let me pull up. Well, while I work on pulling up the chart. But sometimes this is also called V-shaped bent. So I'll just kind of put that in parentheses. So just be aware that there are two basic bents. So again, the water one comes from the tetrahedral family, but then we can have like SO2, where it's just one lone pair, so a little bit different angle. So this is a chart that I was talking about that I'll print out for Wednesday, so you can have this kind of cheat sheet. But this is the second bent here. So notice there's two bents. So the bents, the SO2 bent that we were just looking at, notice that's closer to like 120, right? So kind of that unevenness, and dividing, right, a circle by 360 versus our octahedral one, that's a 104.9 with the bent, or excuse me, 109.4 with the tetrahedral, and then gets smaller with our bent water, right, that goes down to 104. Yeah?
How strict will you be on like quizzes and tests about like what way they're like shaped?
So I won't be too strict for our purposes, like especially again, like I won't have you distinguish V-shaped bent versus regular bent, like just bent is fine. But just kind of, yeah, for your knowledge. And then, so for our class, right, we just have to know our bent shape, trigonal pyramidal, tetrahedral, and trigonal planar. So those are the only geometries we're focusing on. So yeah, this is the only thing you'll be tested on. I just kind of throw out other things because you'll probably hear it, but yeah, in terms of testing, we'll keep it simple. All right, so let's talk about naming and weights, and then probably Wednesday we'll finish up with whatever polarity discussion we need to talk about. And so what's also in here is, okay, well now that we can write our structures and write our names, we want to make our formulas. And so we need to know how to name them. And so now for naming covalent compounds, it's a little bit different, but you may like it. And so unlike our ionic compounds, so again, right, thinking back to our ionic compounds, we always know like sodium's going to lose 1 electron, right? So then we can just name it. Sodium chloride, we always know it's 1+. The problem with our covalent compounds is that we can have many different combinations. So, right, same combination of elements may form many different formulas. And so the one that everyone always gives as an example are all these nitrogen and oxygen formulas, right? So we can't just say nitrogen oxide because we don't know what the heck we're meaning. Is it NO, NO2, N2O, N2O3, right, etc. And that just means for naming purposes, when we just have these compounds made of two nonmetals, then we can use our prefixes. And so then we have our same prefixes that we have for the hydrates, so that little handy cheat sheet I handed out last week with the prefixes, you can use that again. So we have mono 1, di 2, tri 3, tetra 4, penta 5, hexa, hepta, octa, nona, deca. And of course, you can continue on, but. And so we use our prefix, we name our first element, and then use our next prefix again to indicate how many, and then change the ending to "ide" again. And then, so notice, right, we don't usually say like the mono if there's just one of the first element. So now try to name some of those nitrogen ones for practice, and then we'll do. So how would you name those 4 nitrogen combinations? Are we ready to go through them? What do we get for the first one? Say it louder for us, Madison. Oh, dinitrogen. What's the last one though? Just not tetra, but
No, not for trioxide.
trioxide. Oh, no reason.
Panic when you say it loud.
So dinitrogen trioxide. Perfect. I see that in the chat. Second one, what do we get? So dinitrogen oxide or monoxide. So we should use the mono ending for the second one in this case. Then what about NO? So nitrogen and then monoxide. Just make sure you use the mono. And then this N2O4, what do we get? Yep, so dinitrogen, and I see that in the chat now. Tetraoxide. Excellent. Questions on those? Seem fairly straightforward. So hopefully the covalent naming is easier than all the ionic. So now try these 3. we ready to go over these? What do we get for the first one? Isaiah, you want to go for it?
Nitrogen triiodide?
Yeah, so nitrogen triiodide, and that one should have the double I, but I am also pretty generous with spelling too. And then what about B? Raiden?
Phosphorus, let me pull up this sheet. Pentachloride?
Yeah, so phosphorus pentachloride, and Chet agrees with you. And then the last one, yeah. Yeah, tetraphosphorus decasulfide. Excellent. Any questions about those? And so the last bit now is just how to figure out our formula / molecular mass. And so again, part of the beauty of the periodic table and how it's set is that when we look at our mass here, right, this is the mass of either the average of one atom, so right, either it's 12 AMU, or if we're talking about moles, then it's 12 grams per mole. So right, this means that we can figure out the molecular mass of an individual atom or molecule, or we can figure out, right, our molecular mass. And so all this is, again, saying is, so if we do this for a water, and so your numbers can vary, right, with rounding, that's fine. I'm not looking for anything super specific. So if we're trying to find our mass of water, so of course we can look at our periodic table. So we can look at hydrogen. And so, right, it's 1.008 according to this one, right? They rounded, so you can make judgment choices of rounding, that's fine. Just, again, be consistent in your calculations. And then you add it, so of course times 2, and then plus oxygen. And again, right, you might use 15.999, they use 16.00. It's all fine with rounding. And then you add it up, so we can say, right, 1 molecule of water is 18.02 AMU, and again, right, rounding is okay. Or we can say that 1 mole of water has a molecular mass of 18.02 grams, right, and this is always grams per mole when we do our molecular mass. So let's do a little practice. So what's the molecular weight then? And let's just do silicon tetrachloride. So see if you can just figure that out right now. So look at your periodic table, add it all up. What do you get? kind of, what are people getting roughly? You can shout out some numbers at me. Yeah, so that sounds about good. I see in the chat, so 169. I was copying from the chat, so 0.89, and that's grams per mole. So I like that unit, just so again, so you can remember, right, that 1 mole of your silicon tetrachloride has that weight. And I think most people understood it. And again, right, it doesn't have to be this exact number. There's going to be rounding errors. That's fine. Like, I don't want people all stressed out over rounding. Like, that's not the point. Well, let's just kind of recap. So silicon, again, right, just take whatever value you're reading from your periodic table, and then plus our chlorines. So 35.45, oops. And then, of course, multiply by 4, so it looks like everybody did that. And so, yeah, about 169. And then I'm just looking at the chat. Somebody got 172. That looks a little off, so just kind of double check your numbers on there. But like I said, on an exam, I'm not really like, grading you necessarily on your number accuracy. It's your process, and then I can see, okay, you plug those numbers in and you followed the process. Does that make sense for this? I just don't want people like stressed out over the right answer, but. All right. So I think that's probably a good stopping point for today. So I have a meeting after class, so I can't stick around for office hours today, unfortunately, but just email me. I'll be on campus again tomorrow. You can catch me before class. You can catch me in the afternoon. So I'm teaching lab in our same spot, 1:30 to 4:20. Catch me after class tomorrow. So just email me if you need to see me. I'm happy to help you. But I think we're at a good pace right now. I'm feeling good. Wednesday we'll keep reviewing. We'll go over the polar compounds, kind of do more practice. And then, like I said, that'll lead us into Monday to do more practice. So just keep gearing up for the midterm and keep it up. And I'll hang around on stream just in case there's any last minute questions from anybody else. Otherwise, I'll see you on Wednesday. Oh, and then double check that that's not anybody's paper. Missing the homeless homework. Might be somebody online. Yeah. Oh, yeah, I did. I forgot. Okay, now I'll ask the chat if anybody recognizes this. You can always claim it later. I was trying to find a name. All right, no takers on the paper. It's fine. I'll hang on to it until we find its owner. All right, see y'all Wednesday. Thanks for being here, being online. Huh? All right, thank you. I'm going to stop the stream and see y'all on Wednesday.